Hello, Mautas. Well, after taking a ride through the waves, we return to the movement of bodies. Remember that we have this wonderful plan. We take the forces of the system with Newton's dynamics, we obtain the acceleration that we introduce into Galileo's kinematics to get the equations of motion. It's like the factory of motion in physics. Great. So for this course, I propose the following roadmap. And it's nothing more than focusing on this particular force. Of all the forces we can imagine in the universe, we set our sights on one, the gravitational force. This entire course will revolve around that, and we are going to complete this program for this particular case, gravity, from start to finish. So let's see what kind of force gravity is and what kind of movement it produces when we put it into this machine, this factory, and we will do it in our journey with several steps. The first step is to obtain the force of gravity. What is the gravitational force like? For this, we will travel to the past to learn a bit of context. The history of gravity, with two important stops that set us on the path to obtaining the law. One stop is Kepler, the other stop is Newton. Well, without further ado, we begin this course on gravitation, that universal force of the cosmos constantly present in our lives. It binds us to the Earth and takes us on a journey through the cosmos. It is the force that orchestrates the symphony of the planets. As you have seen, we are going to start this course with a brief historical overview that sets us on the path to understanding this force. A bit of context, which I say, if you are interested in going to the equations because you have an exam or for whatever reason, you can skip to the next chapter. So here we ask ourselves, where does it all come from? Well, the truth is that it is very, very ancient. Since the beginning of time, humans have looked to the skies, where they found a great ally to understand changes, those cycles we now know as seasons. The sky was a precious map that served ancient humans to travel through time and anticipate changes, whether it was time for migrations, drought, or rains. The stars were our calendar, very useful information for the survival of our species. Hence, they knew the sky firsthand, and where they drew thousands of stories of gods and mortals that remained etched in their memory. All cultures celebrated their constellations, glorified their particular gods depicted in the skies, but in the West, there was a culture especially eager for knowledge that was not satisfied with that and began to ask more questions. Why the sky and our world? What place do they occupy? How does the cosmos move? We are talking about Greek culture. And they observed something very unique. The stars move in the sky in a circle, completing a cycle of exactly 1 year, after which the same stars reappear in exactly the same place. But there were 5 unruly stars that didn't quite feel like following a cycle. Sometimes they positioned themselves over Taurus, other times over Libra, constantly changing throughout the year. They called these wandering stars planets, from the Greek for wanderer, and they named each one after different gods: Mercury, Venus, Mars, Jupiter, and Saturn, and you might say Uranus and Neptune, but those were not known then. But the question remained, how does the sky work? What place do we occupy ourselves in it? The one who, building on the interesting ideas of his predecessors, would come to bring order to this dance of stars was the greatest sage of the entire classical world. We are talking about Aristotle of Stakyra. With the symbol of the circle as an image of perfection and endowing the heavens with an incorruptible and eternal nature made of a mystical material, the quintessence, Aristotle imagined a world of rotating spheres, a whole set of concentric spheres with the Earth at the very center and the last layer being the sphere of the stars. It is the model that would be called geocentric, an image of great beauty and harmony with a tiny problem. Well, okay, actually it was a big problem, which is that it is not correct. That is, if you look at the sky, you see day after day that the planets do not follow perfect circles. And Aristotle already knew this, because these people, as I tell you, were not foolish at all. But he didn't give much importance to this, because what he saw with his senses, he knew deceived him. Pure reason is capable of better understanding reality through beautiful ideas. So it's better not to look and not to compare, and to listen to reason, to intuition, which speaks to us of a perfect world moved by spheres. Well, someone who did look, and looked very well, was another classical scholar, Claudius Ptolemy, a Greek astronomer and mathematician who worked in Alexandria about 2000 years ago. Okay, Ptolemy compiled the most important and precise star catalogue of his time, and inspired by Aristotle and Plato, created a geometric geocentric model to make sense of it, no longer based on reason, but on observation. So he took this geocentric model from Aristotle and modified it so that it now fit the data. He added extra movements, equants, deference, epicycles, a whole complicated framework to make the model work with reality, with what was observed. And he certainly succeeded. His vision would last for more than 1,500 years. And even though his writings were lost, they were recovered by the Arabs, who preserved them for posterity under the name Almagest, the book of Ptolemy, literally the greatest. Well, this is the Aristotelian Ptolemaic view of the cosmos that dominated Western thought until the birth of modern science, largely because it was embraced by the Christian Church as the model of the world, as the truth. But everything was about to change with the arrival in the world of one of the most important figures in history. And I am not exaggerating. He is the Paul Nicholas Copernicus. Born in 1473 in Poland, orphaned at an early age, he was tutored and protected by his uncle Lucas, who would become the Bishop of Warmia. I said Warmia, not Guarnia, see that, and that bad he was tempted. Oh yes, Copernicus had a broad education in medicine, law, languages, and astronomy at the main universities of Europe, such as Bologna, Padua, or Rome. Laterly, he would be named a canon like those green lettuces. Well, and he returns to his country where he would work in the administration of the Diocese of Warmia and where he would remain for the rest of his life. And although his occupations covered a bit of everything from medicine to law or administration, his true passion, you know what it was, astronomy, in which he was going to produce an earthquake that would change everything, forever. His great work is a project of more than 25 years, although it actually spans his entire life and is one of the great masterpieces of history. De Revolutionibus Orbium Coelestium, a work he was very careful to publish with approval after being reviewed with a clarifying preface and dedicated to the Pope, and in any case, always printed after his death. By the way, there is an interesting historical controversy about the preface where it is clarified that it is only a mathematical model and does not intend to represent reality, but it seems that it was not Copernicus who wrote it, but his editor without his consent. And why was this work so important? Because it represented a true revolution in the way we see our world. Copernicus places the sun at the center and the Earth as just another planet orbiting the star. It is the heliocentric model as opposed to the geocentric model of Aristotle and Ptolemy. The impact of this idea was so profound that today, when we want to say something has been very impactful, we say it has been a Copernican revolution, which is no small thing. What would have been Copernicus's motivations for doing something like this? Well, he had observed deviations, inaccuracies in the Ptolemaic model, which prompted him to try a different arrangement that was cleaner and more elegant. Now the bothersome epicycles and all that apparatus that Ptolemy artificially added to make things fit well were no longer necessary. We can now return to the Greek perfection of circles. But friends, it was not going to be as simple as you might expect.
Yes, that's what and this new idea, which really wasn't so new because the Greek Aristarchus of Samos had already proposed it about 2,000 years earlier, well, this new idea also had to overcome new obstacles.
First of all, because it went against the scriptures and the church's dogma with the earth and humans at the center of the universe. Secondly, because it implied that the earth moved, and that was nonsense. And I don't think we can blame our ancestors for thinking that way, considering that if you look around, it doesn't seem like you're moving. And thirdly, and very important to keep in mind, it did not improve the Ptolemaic model with respect to the observations. The data still did not fit perfectly. The first was a sociological, cultural issue. Very tricky, but the next two had solutions. So let's focus directly on them, and knowing that for each of them, there would be one of our great heroes. On one hand, the Italian astronomer, inventor, and mathematician Galileo Galilei, one of the greats in history. He fell in love with Copernicus' idea at the university and fought with effort, tenacity, and courage to convince the world of its truth. In particular, he worked on the second issue, that of how the Earth can move if it's not what we see. He studied motion to prove that if everything moves together, we wouldn't notice anything. It's not that the Earth doesn't move, it's that it drags everything with it, and that makes us not feel it. It's what we know today as Galileo's relativity and leads to that famous first law of Newton, the law of inertia. Additionally, he accompanied his studies of motion with pioneering observations of the sky, using a new instrument that he brilliantly perfected. I am talking about the telescope with which Galileo saw the moons of Jupiter, the phases of Venus, the sunspots, or the craters of the moon, discrediting many old ideas inherited from Aristotle about the perfection of the heavens or the movement of the moon around the earth.
Galileo also represents a struggle of reason against dogma, which is why he has also gone down in history with that.
We already had a good answer for the second obstacle to the heliocentric theory. The Earth moves, even if we don't notice it, because movement is relative and the Earth drags everything, it moves with it. For the third obstacle, remember, the heliocentric model does not improve on the geocentric one regarding observations. We have our German hero, the first great modern astronomer.
I'm talking about Johannes Kepler. Kepler's story could make for a Netflix series with many seasons, all in the style of Game of Thrones, but I'll summarize his particular plot a bit for you.
We are talking about a brilliant mathematician in love with the Copernican model and the heavens with one major flaw, his eyesight. As a child, he had smallpox, which left him with a chronic vision problem. We are talking about an almost blind astronomer, imagine that. So he needed good observations, the best he could get, and he had them because the best observational astronomer of his time, this gentleman here, who had his own quirks, Tycho Brahe.
The opposite happened to Brahe compared to Kepler. Thanks to royal favor, he had the best means to observe and measure the skies, but he lacked the mathematical brilliance to put everything in order. So there was a match. But it was not going to be easy, because while Kepler was a convinced Copernican, Brahe rejected those new ideas, so they needed each other and at the same time avoided each other. They worked together, but with much distrust, until Brahe suddenly died. He may have been poisoned, we will never know. Kepler took his position and his data. With them and thousands of nights locked away pondering, he arrives at his great masterpiece. We are talking about Astronomia Nova and also Harmonice Mundi, where he publishes his famous 3 laws of planetary motion, Kepler's 3 laws, that planets do not move in circles but in ellipses, that in doing so they sweep out equal areas in equal times, and that the square of the period is proportional to the cube of the radius of the orbit. Calm down, if you didn't catch it, I'm not surprised, it went very fast, and it's not easy at all, but we're going to dedicate a whole chapter to these laws, so easy. Now everything was in its place. Thanks to Kepler, the Copernican model with elliptical orbits already perfectly matched the observations, clearly showing the superiority of the heliocentric model over the geocentric one. It is not only simpler and more beautiful, but also more precise. And thanks to the other genius Galileo, we know that not perceiving the movement is not a problem either. Movement is relative. So everything was set already for the final blow. A theory that would explain these movements, and it would. Who would it be? Well, the greatest among the greatest, the Englishman Isaac Newton. Newton inherited this situation. 3 laws that describe the movement of the planets very well. And a big question, how do they do it? To this question, Newton would dedicate many years of his life, culminating in a theory of motion capable of explaining both the orbits of the planets and the fall of an apple. But let's take a look at Newton. Newton had an unhappy childhood, raised by his grandparents, misunderstood, with difficulties in socializing, and a universe in his head that overflowed everywhere. His place was clearly in books, in study, and he achieved it. He entered to study at Cambridge, proceeded to PhD, where his only motivation in life was to study obsessively and compulsively. This is how he became the best mathematician of his time and surely of all time. But his great creative work would take place under special circumstances, confined to his family estate after a pandemic of the Black Plague forced the university to close. These are the years of 1665 and 1666, which I remember by heart because they are now a symbol of physics for everything this man produced in those years. But very particularly concerning the development of this story, he did 2 very important things. On one hand, he obtained the laws of motion, the famous 3 laws of Newton. But on the other hand, he also obtained the law of universal gravitation, that famous equation that explains the force of gravity, both the fall of an apple and the dance of the planets in the cosmos. He would publish it years later in what is considered the most important work of all time, the Mathematical Principles of Natural Philosophy. A masterpiece that established him as a true legend and laid the foundations of this force of gravity. Finally, we already had an understanding of the movement of the celestial bodies guided by that invisible universal force. If the planets revolve around the sun, it is because of that mutual force that binds them, and due to inertia in motion, makes them rotate. And this, friends, is the context in which the theory that describes this universal force is born to understand the cosmic order, how our world moves, and what place we occupy in it. As you can see, it was not easy, but the impact on our world made it worthwhile, and this achievement was not just a scientific achievement of mastering a force mathematically, of understanding the dynamics of the planets. It was much more. It was a change of mindset. A new world was opening, guided more by reason, a new mentality that was more critical and objective. Human beings gradually found their place in the universe. They were no longer the center of everything, the measure of all things. These new ideas forced us to change our mindset, an impact much more than merely scientific. A new era was inaugurated with a great ally, scientific thought, for we are now ready to dive into the technical part of this course to discover the wonders of this force, the force of gravity. And let's start at the very beginning. You already know, Kepler's laws. See you there.